This study unit covers the basics of input-output programming. In this unit, you will see how instruction and addressing modes, described in previous units, are used by the CPU to communicate with peripheral devices. Two major topics will be discussed. First, we will talk about the programming of peripherals. We'll see how the processor uses instructions to send and receive data and control information over the Unibus. The second topic is program loaders, what they're used for and how they work. We'll take apart the Bootstrap loader, which we've seen before, and find out how it performs its very important function. Up until now, we've talked about instructions, the different addressing modes, and how several instructions can be grouped together to form small programs or routines. However, the discussion was mostly oriented to internal CPU operations. For the most part, we ignored the rest of the computer system, the peripheral devices. Now, we'll see how different instructions are used by the CPU in a computer system, a system that consists of the CPU and its associated peripherals. System communications are between DMA devices and memory, or between non-DMA devices and the CPU. As you recall, DMA devices, such as disks and magnetic tape units, use non-processor requests to bypass the CPU when data is transferred. Non-DMA devices, such as the teletype, on the other hand, communicate with the CPU by means of bus requests, or BRs. Our talk on I/O programming will pertain to this latter category of peripherals, the non-DMA type devices. Peripherals are composed of two essential units, the peripheral itself and an interface unit that ties the device to the Unibus. The interface unit is also referred to as a control unit or controller. Depending on the particular device, the interface may be located within the peripheral or at some other location, such as the processor box. The majority of PDP-11 interface units perform four basic functions. The interface recognizes the unique address associated with the device to determine if the device has been selected for use. Then, when the peripheral is ready to accomplish its assigned task, the interface gains control of the bus and interrupts the processor operation. The interface also has the ability to control and monitor the peripheral operation. Finally, the data to or from the peripheral is temporarily held or buffered in the interface. Let's look at these last two functions, control and buffering, more closely. The interface contains two important elements that are used for device control and data buffering. The device control tells the peripheral what to do and then monitors the operation to find out when it is finished. Errors are also kept track of by the control circuit. The data buffer holds the data from the Unibus until the peripheral is ready to use it. It also buffers data from the device until it can be placed on the Unibus for transfer to the CPU. The data buffer register, or DBR, is used in most peripheral interfaces for temporary data storage. The number and size of data registers is determined by the particular device. Almost all DBRs are either 16-bit word buffers or 8-bit byte buffers. Data transfers between the Unibus and the data buffer register, or DBR, are always in parallel. Many devices, such as the teletypewriter, are serial in nature. Data is transferred serially between the teletype and its DBR. From this, we can see one of the primary functions of a DBR, to provide serial to parallel conversion of data sent from the peripheral to the Unibus and parallel to serial conversion for data moving in the opposite direction. Another function of a DBR is to compensate for slow devices. Many devices operate at relatively slow speeds. Rather than hold up the Unibus for long periods, the interface holds the data in the DBR until it is completely assembled and ready for transfer. The Control and Status Register, or CSR, is a 16-bit register used in all peripheral interfaces. It performs both command and monitoring functions. Some interfaces contain two CSRs, one for command and one for monitoring. The CSR is loaded with command or control information from the CPU. Either a data O or data OB cycle can be used to accomplish this. The CSR then exercises direct control over the peripheral's operation. The CSR also stores status information that pertains to the peripheral device. The central processor can then retrieve this status information by initiating a data I bus cycle. The CSR is byte addressable. In general, the low byte is used for commands and the high byte is used for status. Since peripherals differ, their associated interfaces are structured differently. Some require more CSR bits than others. Normally, the CSR bit assignments are as shown here. In the low byte, bit 0 is the start or enable bit. It begins device operation at the time it is set. Bits 1 to 3 specify one of 8 possible device operations. Bits 4 and 5 are required for those devices that use the extended 18-bit address. Bit 6, when set, allows an interrupt to be asserted on the unibus. Bit 7, indicating the peripheral is done already, causes an interrupt providing bit 6 was previously set by the CPU. The high byte holds the status information. Bits 8 to 10 are used to select the device if more than one device is controlled by the interface. Bit 11 indicates when the addressed device is busy and therefore not available. Errors are indicated by bits 12 to 15. Bit 15 is used if the device has only one error flag. Otherwise, bit 15 is the inclusive OR of the other error bits. A typical CSR might use 4 of the 16 bits: error, done or ready, interrupt enable, and start. There are 3 types of bits used in CSR registers: read-only, write-only, and read or write. Bits 7 and 15, as shown here, are read-only bits. They can only be read to the unibus. Writing into a read-only CSR bit has no effect on the bit condition. It remains in its previous state. However, data could be lost if the programmer had expected to store data in a read-only bit position. Bit 0 is a write-only bit. It can only be loaded from the unibus. Since a write bit is always read as a 0, we can never read its status. There's no way to determine if the bit position actually contains a 1. Bit 6 is a read or write bit. It can be loaded from or read to the unibus. A load command, such as a move byte instruction, is used to set the appropriate bits in the CSR. The move byte instruction generates a data OB, and the selected bits are placed on the unibus data lines. In this example, bit 0, start, and bit 6, interrupt enable, are set in the CSR during the data OB. When the CPU wants to check on the condition of the peripheral, it issues the appropriate instruction. Here, a data I, which could have been generated by a move instruction, conveys the CSR status bits to the CPU. Can you tell what occurred in the peripheral? That's right. A parity error was detected, as indicated by bit 15 being set, and now the CPU is informed of this error condition. The CSR and the DBR work together in most I/O operations. Let's look at an example of this. We'll assume that the CPU has decoded an instruction which tells it to read a byte of data from a peripheral device. To start the operation, the CPU sets appropriate control bits in the CSR. In this example, the CPU initiates a data OB cycle to the CSR and asserts bits 0 and 6 on the unibus data lines. As a result, both the start and interrupt enable bits are set. The read operation in the peripheral begins when the start bit is set. If our peripheral happens to be a serial device, such as a teletype, it then starts to serially read the data byte into the DBR. The done bit is set as soon as the entire data byte has been brought into the DBR. Since the interrupt enable bit is already set, the done bit causes an interrupt to be sent to the CPU. The interrupt notifies the CPU that the requested data is available. The CPU then shifts to an interrupt service routine in the program and services the DBR by issuing a data I. As a result, the data is sent in parallel to the CPU via the unibus. The done bit is cleared at this time. Although we've just gone through a generalized description of an I/O sequence, It does show how closely the DBR and CSR work together. It's a very interdependent operation. We'll look at it again in more detail later on. Let's sum up a couple of points about these two interface registers, the CSR and the DBR. All interfaces have at least one CSR to command and monitor the peripheral operations. Most interfaces have a DBR to hold read or write data. Various combinations of CSRs and DBRs can be used. For example, an interface might have two CSRs and two DBRs. One CSR would be used for command and the other for status. The DBRs could also be dedicated according to function, one for load data from the CPU and one for read data to the CPU. Register usage is determined by the nature of the peripheral. Some interface units also have one or more special purpose registers. We won't talk about these registers in any detail, but let's find out what the names of some of them are. In addition to the CSR and DBR, an interface could also contain a word count register, a memory address register, a data address register, and a maintenance mode register. These registers are typically associated with DMA devices. The word count register keeps track of the number of words transferred by the interface. The memory address register specifies the location in memory where data is to be loaded or taken from. The data address register is used for referencing storage locations within mass storage devices such as disks and magnetic tape units. The maintenance mode register is used for various command and status functions associated only with the maintenance of peripheral operation. There are three generally defined operations that take place in the interface during a program data transfer. First, the interface must receive and recognize the address of the selected device register. At the same time, the CPU specifies the type of operation, say a data I or a data OB, that is to be performed. Finally, the transfer of data is effected. The interface either receives data from the CPU or transmits data to the CPU. The DBR is used in both instances. Let's consider the first of the three operations, addressing. Each peripheral interface register has been assigned a specific address. This address is located in the top 4K of possible addresses and is not repeated in core memory. As far as the CPU is concerned, an address is an address. It makes no distinction between memory locations and peripheral registers. CSRs and DBRs can be accessed as easily as core memory. Processors that use 16-bit addresses have a usable memory space that is limited to the first 28K word addresses. The next 4K, starting at 160000, is used for 16-bit register addresses. These register addresses are converted by the CPU to 18-bit addresses that reside in the highest 4K of the address space. A peripheral address is indicated if bits 13, 14, and 15 of the 16-bit address are ones. The CPU then converts the 16-bit address to an 18-bit address. When the conversion takes place, bits 16 and 17 of the 18-bit address are set to ones. Therefore, all peripheral addresses start with 77 or 76, which denote the highest 4K of the address space. This 18-bit address is the one that the interface responds to. The address decoder in the interface is interested primarily in the address bits which specify the peripheral, namely bits 3 through 12. This is understandable since bits 13 through 17 are always all ones. The three lowest order bits, 0 through 2, do not figure in peripheral identification. The particular CSR or DBR within the addressed interface is determined by bits 1 and 2. The address shown here identifies one of the teletype registers. Let's look at this a little more closely. The teletype interface has 4 registers, 2 CSRs and 2 DBRs. Notice the similarity of the register addresses. Only the least significant digit is different for each register. The address that we have decoded, 777560, is for one of the CSRs. The last bit in our address, bit 0, defines the type of operation that is to take place, either a word or a byte operation. The teletype is actually 2 units that operate independently. the paper tape reader keyboard, and the paper tape printer punch. Each unit requires a separate CSR and DVR. One of the teletype DVRs is assigned to the printer punch unit. The other DVR is assigned to the reader keyboard unit. In performing a data O or data OB, the printer punch DVR temporarily stores data from the CPU before it is output to the printer and punch mechanisms. On the other hand, when performing a data I, the data originates at the paper tape reader or the keyboard and is temporarily stored in the reader keyboard DVR before it is transmitted to the CPU. If we take a closer look at the reader DVR, we see that the data is input to the register serially from the teletype and then output in parallel to the Unibus. Data is transmitted over the Unibus 1 byte at a time. Notice that we only use the lower half of the DVR for storage. The code shown here, 301, represents a capital A. Characters and numerals are coded on tape in the ASCII format. Our A character has a code of 101. However, the teletype transmits in the teletype code. The A now has a code of 301. The character is stored in memory in this format and later changed back to the ASCII format by the computer program. An instruction in the program does this by subtracting 200 from the stored information. Data flow through the printer punch DVR is in the opposite direction. Write data from the Unibus enters the printer punch DVR in parallel format. It is then serially transferred to the teletype. The code shown here, 264, is the teletype code for the number 4. Of the two CSRs in the teletype interface, one is used with the printer punch unit and the other with the reader keyboard unit. Both CSRs receive command information from the CPU via the Unibus. Data O or data OB cycles are used for this. The central processor initiates a data I bus cycle if it wishes to read status information that is stored in either one of these CSRs. The teletype CSRs are referred to as the punch status register, or TPS, and the reader status register, or TKS. The bit assignments are similar to the examples that we previously discussed. One that we didn't describe before is bit 2 of the punch status register. This is called the maintenance bit. The maintenance bit, when set to a 1, causes the data in the punch data buffer to loop back to the CPU via the reader data buffer. It still goes to the punch, but by also echoing it back to the source, the CPU, we can check both the transmitter and receiver functions of the teletype interface. It's a simple matter to check the return data against the data originally sent to the punch. The other punch status register bits should be familiar to you. If interrupt enable is set, an interrupt is allowed when ready is asserted. This occurs when the punch data buffer is available to accept data. Ready is then cleared when the punch data buffer is loaded. 4 bits are used in the reader status register. By setting bit 0, reader enable, we can direct the paper tape reader to read 1 character. The keyboard is not affected. Interrupt enable allows an interrupt when the done bit is set. Done is set when a character is available in the reader data buffer. It is cleared by any program reference to the reader data buffer, or when the reader enable bit is set. The busy bit denotes the reader condition. It is set by the start of the data stream from the paper tape and cleared when done is set. Suppose we take another quick look at the teletype device registers. There are 4 registers, 2 CSRs and 2 DVRs. Each has a unique address, as shown here. The CPU selects a register by placing its address on the Unibus. The teletype reader, CSR, and DVR operate independently of their counterparts in the printer punch. The PDP-11 uses a common set of instructions. The same instruction can be used with memory and peripheral registers. Furthermore, as we noted a while back, the CPU makes no distinction between memory addresses and register addresses. PDP-11 instructions can address and operate on the contents of a CSR or DVR in the same way that they operate on the contents of memory locations. The program can move data to or from a DVR. It can increment a CSR, or it can do a number of other things. Let's look at a few examples of instructions that involve the teletype register. Do you recall how we initiate a read operation in the paper tape reader? That's right. We simply set the reader enable bit in the reader status register. One way to do this is by incrementing this register. The reader enable bit, which is the least significant bit, is always cleared when data is read from the tape into the DVR. Therefore, this bit is in the clear state at the conclusion of every read operation. Thus, an increment or increment byte instruction addressed to the reader status register always sets the reader enable bit. Another way to set one or more bits of a CSR is to move a data byte into the register. Here, we're using the PC immediate mode to set both the reader enable and interrupt enable bits. This instruction will start the reader and then allow an interrupt as soon as the data is in the reader buffer register and the done bit is set. The reader status register is identified as TKS at some other point in the program. A move instruction can also be used to transfer data either to the peripheral or from the peripheral. Here, we're doing a move byte to transfer data from the reader buffer register, which has an address of 177562, to a general purpose register, in this case GPR3. Remember now, all data and control signals to or from the peripheral are via the Unibus. That includes our friend here, the letter A, which is represented by the code 301. The test byte instruction is another example of how device registers are used the same way as core memory locations. When addressed to the punch status register, as it is here, the test byte instruction will set the N bit in the processor status word as soon as the ready bit, bit 7, is set. Remember, bit 7 is the sign bit for the low byte. If the test byte instruction is followed by a branch instruction that tests the state of the N bit, the program can be made to loop until the ready bit is asserted. We'll see an example of this later on. Let's take a short break now. When you come back, we'll find out how to use these instructions we've been talking about.